Resource recovery from biosolids. Observed fact. In regulatory and technical literature, biosolids is the term commonly used for sewage sludge that has been treated to meet regulatory requirements and prepared for land application as a soil amendment or fertilizer as one. The word matters. It separates raw, untreated sludge from material that has passed stabilization, monitoring, and quality checks. Why focus on solids? Because the solids line in a wastewater treatment plant carries concentrated organic matter, nutrients, water, pathogens, and a portfolio of chemical contaminants. That concentration is what makes the stream both a resource and a risk. Viewed as a resource, biosolids can return carbon and nutrients to soils, generate energy through biological conversion, and yield recoverable minerals. Viewed as a risk, the same concentration can concentrate pathogens, persistent organic contaminants, including per- and polyfluoroalkyl substances, PFAS, metals, and other compounds of concern that require management under public health and environmental standards. 1.2. Stated assumption. A robust management strategy treats characterization and risk assessment as the starting point for any recovery pathway. In practice, the choice of stabilization, energy recovery, or nutrient reclamation must reflect the physical and chemical characteristics of the solids and the legal framework within which the utility operates. This episode will follow the solids from separation to reuse options, clarifying where evidence is firm and where trade-offs require practitioner judgment. Observed fact. Primary and secondary treatment generate a spectrum of solids: primary settlable material, biological solids from secondary processes, and screenings and grit upstream. These streams are commonly combined, thickened, and dewatered before further treatment or disposal. 3. What must be measured? The operational decision hinges on moisture content, volatile solids or organic fraction, nutrient concentrations, principally phosphorus and nitrogen, pathogen indicators, and the presence and concentration of chemical contaminants, including metals and emerging substances such as PFAS. Variability over time, seasonal loading, industrial discharges, storm events, alters the available options. A solid stream with high organic content is more favorable to biological energy recovery. A stream dominated by inert ash or mineral inputs is not. Illustrative example. A utility evaluating anaerobic digestion will prioritize measurements of biodegradable organic matter and solids retention time dynamics. A utility considering land application will focus on pathogen indicators, vector attraction potential, metals, and regulatory parameters. These are not mutually exclusive. A solids management plan often layers options according to the outcomes of characterization. Observed fact. Regulatory frameworks condition which end uses are permitted. In the United States, 40 CFR Part 503 sets standards for land application, surface disposal, and incineration, including pathogen reduction and pollutant limits, along with monitoring, record-keeping, and reporting obligations. 4. Characterization must therefore be designed to generate data that demonstrate compliance with applicable regulations. Recommendation. Begin any recovery evaluation with a formal sampling and analysis plan tied to decision thresholds. What contaminants need confirmation, how frequently, and which analytical methods are required to support a chosen reuse or treatment pathway. This plan should include an assessment of uncertainty and a pathway for supplemental sampling when values approach regulatory or market thresholds. Observed fact. Stabilization technologies aim to reduce pathogen risk, control odors, and improve handling characteristics. Common processes include anaerobic digestion, aerobic treatment, thermal conditioning, and chemical stabilization. Each approach changes the biosolid's physical and biological profile in different ways. 3. Anaerobic digestion works by converting biodegradable organic matter into biogas under oxygen-free conditions. It also reduces pathogen indicators when operated under validated time temperature regimes and process controls. Aerobic stabilization uses oxygen and microbial oxidation to convert organic matter, but can demand more energy for aeration. Thermal and chemical treatments can achieve high levels of pathogen reduction and vector attraction reduction, but they impose capital and operational costs and may alter the material's suitability for some end uses.
Observed fact. The POC 503 regulation contains operational requirements tied to pathogen reduction and vector attraction reduction for biosolids to qualify for certain land application pathways. Compliance involves prescribed monitoring and documented process controls, rather than a single technological solution. Stated assumption. The best stabilization work balances pathogen control effectiveness with energy consumption, operational complexity, and the intended end use. For example, a system that aims to supply a marketable soil amendment may demand treatments that preserve agronomic value while meeting pathogen and contaminant criteria.
Recommendation: utilities should document stabilization goals explicitly. Is the priority pathogen reduction, vector control, dewatering for transport, or preservation of plant-available nutrients? The choice of technology should follow from those priorities and from the material characterization described earlier. Observed fact: biosolids contain organic carbon that can be converted to energy through biological and thermal routes. Anaerobic digestion produces biogas, which can be used directly for heating, upgraded to biomethane, or consumed in combined heat and power (CHP) systems. Thermal processing and incineration release energy, but change the material stream and can concentrate certain contaminants in ash (S3). Caveat: the research log identifies an open gate for quantitative claims. Without a peer-reviewed or technical source applied to a defined system boundary, this narration will not present numerical performance figures. Any numerical claim requires documented mass and energy balances tied to an operating example and a vetted reference. Therefore, this chapter will describe trade-offs qualitatively. Energy recovery reduces net fossil fuel demand when the recovered energy displaces external energy. However, the energy required for preconditioning, thickening, dewatering, thermal drying, and for downstream treatment of emissions or residues can offset gains. The carbon balance depends on whether energy recovery displaces fossil-derived power or simply shifts energy burdens within the treatment plant. Illustrative example: a plant with stable flow and high volatile solids is often a good candidate for anaerobic digestion and on-site CHP, because the biogas can satisfy heat and power needs. Conversely, plants with low biodegradable fraction or with large quantities of inert solids may find thermal drying or direct disposal more realistic, accepting that the energy input for drying can be substantial. Recommendation: before selecting an energy recovery route, develop a system boundary and a verified mass and energy balance. Include all internal energy uses, parasitic loads, and potential for cogeneration or off-site energy sale where regulations permit. This step is a gate. Without it, claims of net energy benefit remain hypothetical. Observed fact: biosolids contain concentrated phosphorus and nitrogen. Phosphorus, in particular, is finite at planetary scale and has motivated a range of recovery technologies from direct land application to extraction and concentration techniques. The utility of recovered nutrients depends on yield, product purity, and market acceptance, S3. Trade-offs are central. Methods that concentrate phosphorus, for example through chemical precipitation and subsequent processing, can produce materials suited to fertilizer markets, but they may require chemicals, energy, and produce residuals. Land application returns nutrients in a broadly distributed form, supports soil organic matter, and avoids chemical processing, but regulatory limits and public acceptance can restrict this pathway. Stated assumption: product specifications and market context drive the economics and feasibility of nutrient recovery. Utilities must weigh whether to produce an engineered fertilizer product, an ash-derived phosphorus concentrate, or to rely on agronomic recycling through regulated land application. Illustrative example: recovering phosphorus as a mineral-like product can increase transport efficiency and market value, but it typically involves steps that change the biosolid's composition and may require thermal treatment or chemical additions. Returning biosolids to farmland supports soil health, but places more emphasis on meeting contaminant and pathogen criteria. Recommendation: structure nutrient recovery evaluation around 3 questions.
What form of nutrient is required by potential end users? What quality and contaminant specifications must be met? And what are the local regulatory and market constraints? A pilot program with product testing under real-world agronomic use is an essential intermediate step before full-scale conversion. Observed fact: emerging contaminants, particularly PFAS, have shifted the decision framework for biosolids management. EPA recognizes PFAS as an area of research and potential risk in biosolids management, and EPA's Biosolids Research Program evaluates the environmental and health implications of such contaminants, S1, S2. Distinguish detection from risk. Analytical capabilities now detect many compounds at trace levels, but detection alone does not prescribe a single treatment strategy. Risk assessment requires understanding exposure pathways, fate and transport, and the effectiveness of candidate treatments in reducing risk. Some treatments may redistribute contaminants, for example, transferring them into ash or into separated liquid streams, rather than destroying them. Observed fact: current guidance and research at EPA and in the wider scientific community emphasize targeted assessment of contaminants of concern, prioritize research on effective removal or destruction technologies, and the need for clear communication with stakeholders, S2.
Recommendation: utilities should adopt a precautionary approach while evidence evolves. Conduct targeted monitoring for contaminants of concern. Document mass flows for contaminants through treatment steps, and avoid unilateral claims of contaminant removal unless supported by robust, peer-reviewed data. Engage transparently with regulators, downstream users, and the public. Provide the data that link process steps to contaminant fate. Observed fact: the research log and practice guidance recommend a sequence of actions. Characterize the feedstock. Define regulatory and end-use requirements. Compare stabilization and recovery options. Test mass and energy balances. Validate product quality. Plan monitoring. And then implement a path that preserves options where feasible. S3, S4. Here is a practical sequence adapted for engineers and managers. Characterize: baseline sampling for moisture, organics, nutrients, pathogen indicators, metals, and targeted emerging contaminants. Assess variability and critical worst-case inputs. Define constraints and goals. List applicable regulations, targeted end uses, market specifications, and institutional constraints, landscape, energy availability, capital. Screen technologies. For each candidate treatment, document how it affects pathogens, nutrients, contaminants, energy flows, and operational complexity. Quantify flows. Develop mass and energy balances for the most promising options. If numerical claims are to be presented publicly, base them on peer-reviewed or vetted technical sources and documented operating data. Pilot and validate. Run pilots that test both process performance and final product quality under representative conditions. Include analyses required by regulators and by potential buyers or land managers. Plan monitoring and records. Design a monitoring program sufficient to demonstrate compliance and to detect process excursions. Include contingency protocols for non-compliance. Choose reversible or stepwise implementation. Where uncertainty is high, select modular or reversible technologies that allow shifting course as new evidence, for example on emerging contaminants, becomes available. Recommendation: treat the framework as iterative. New monitoring results, regulatory updates, or market changes should trigger a reevaluation. Preserve data and transparent documentation to support adaptive management. Observed fact: there is no single engineering prescription that fits every utility. Site-specific feedstock properties, regulatory frameworks such as 40 CFR Part 503, energy and market contexts, and public acceptance all interact to shape feasible pathways. S4. Stated assumption: recovery creates durable value when it reduces net environmental burden, meets regulatory and safety requirements, and supplies a credible end use or displaces fossil-based inputs. Conversely, recovery can be counterproductive if it locks a utility into capital and operational commitments that transfer rather than reduce risk, or if it produces a product that markets will not accept. Illustrative example:
A plant that can produce a stable, well-characterized biosolid product with documented contaminant profiles aligned with local agricultural needs may achieve circularity by returning nutrients to soils. Another plant, facing high levels of emerging contaminants without available destruction technologies, may find that controlled disposal or thermal processing with appropriate emissions control is the more defensible path. Recommendation: before committing to a recovery pathway, apply the decision framework and assemble an evidence package that includes feedstock characterization, validated process performance, a verified mass/energy balance, product testing aligned with regulatory and market criteria, and a monitoring plan that documents sustained compliance. Communicate the evidence openly to regulators and stakeholders. Final checklist for practitioners: transparent and non-prescriptive. Characterization: do you have representative sampling and documented variability? Regulatory mapping: which legal standards apply to your intended end use? Stabilization target: what pathogen and vector controls are required? Energy accounting: have you established system boundaries and a verified mass/energy balance? Nutrient strategy: what nutrient forms and purities do your markets require? Contaminant plan: have you tested for contaminants of concern and planned for their fate? Pilot validation: have you piloted the process and validated product quality? Monitoring and records: is there a monitoring program that demonstrates compliance? Reversibility: can you change course without prohibitive cost if new evidence arises, for example, on emerging contaminants becomes available? Observed fact: the research gaps noted in this episode are real and operationally significant. The literature curated for this script highlights regulatory context and programmatic research priorities, but it does not yet supply peer-reviewed, system-bounded numerical performance data, or an operating example with verified mass and energy balances. Those data are necessary to move from qualitative guidance to prescriptive engineering design. Recommendation: utilities and engineering teams should treat the absence of those data as a call to rigorous pilots and transparent documentation. Only with site-specific measurements, documented pilot runs, and third-party validated analyses can numerical claims be responsibly made and relied upon.
This episode has traced the solid stream from definition through characterization, stabilization, energy and nutrient options, contaminant challenges, governance, and decision-making. The central engineering question remains: does recovery create more durable value than disposal for a given utility under its specific constraints? The answer is not universal. It is a decision arrived at through careful measurement, transparent evaluation, and adaptive management.